Welcome back, everyone, to the eCoreAcademy e-learning platform. My name is AJay Raj, back with yet another Algebra 1 video for you all, and today's lesson topic is all about geometric sequences. So in this video, we're going to discover what geometric sequences are and how to represent them through equations, the two major types of formulas, your recursive and your explicit formulas, just like you would with arithmetic sequences. Before we jump into today's video, please make sure to do 4 things. Please make sure to smash that subscribe button, hit that like button, turn on post notifications, and drop a comment down below. All of those things really help. So let's take a brief overview of exactly what geometric sequences are. So what exactly are geometric sequences, and how do they play an important role in gauging Algebra 1 concepts and also building up with the current lesson and chapter that we're going over that has to do with building up to exponential functions, which we'll also visit later in Algebra 2. So geometric sequences, a basic definition. A geometric sequence is a sequence of values where each term in the sequence increases proportionally by multiplying a common ratio. Now, think about an arithmetic sequence. An arithmetic sequence is basically represented by a linear equation. You can always represent it like that graphically. You're always increasing by a certain factor, you're adding that certain factor to every single term to get the next term, or you're subtracting to go backwards. Say, for example, you start with 2, and then you have a common additive factor of 2, then you're going to add 2 going on and go so on and so forth as a common difference. So 2, 4, 6, 8, 10, so on and so forth. And you can also go reversed. You can call it -2 as your common difference. So then you're going to go 2, 0, -2, -4, -6, so on and so forth. But with geometric sequences, it's actually a little bit different. Instead of adding and subtracting, you're just going to be multiplying with geometric sequences. So you have a starting point in your sequence, your starting term, and you're going to be multiplying a common ratio, something that you're going to multiply to each term to get the next term. Geometric sequences help in identifying exponential growth, in which there is always a constant increase or decrease. So think about an arithmetic sequence. An arithmetic sequence is always linear. You're adding or subtracting. When it comes to geometric sequences, it's exponential. So what happens is you always have a constant increase or decrease, and it's not always the same amount that you're going to be increasing by. You're increasing by the same factor, however. So if you think about an exponential curve, essentially, you have an asymptote and you're just spiking up or sparking downwards. That's the essence of an exponential function. But this is the basic format, just looking at it in numerical terms. You can create rules for geometric sequences through a recursive and explicit formula. Both of those are also applicable for their specialized purposes, which we will also go over in this video. And for sequences, you can create them just like your arithmetic sequences. There's a specialized format of recursive and explicit for your arithmetic sequences as well. Excuse me. So geometric sequences are collections of correlating numbers. They're not necessarily your equations or any of your rules. You're creating the rules for your sequences. They're just sets of numbers, and you identify their properties. And they also have the same graph as exponential functions. They have the same properties as exponential equations when you write them in your format of recursive or explicit, but they also have the same exact graph. So they really are just exponential sequences. Alright, so now let's look at creating sequence rules. We're going to learn how to identify what our common ratio is and how to essentially making a formula that identifies an entire sequence, just like you would for a graph identifying a linear or exponential equation. So let's find the rule for the following sequence. So this is sequence A that we're given. It has the terms 2, 8, 32, and 128. Remember, we're trying to find a common factor that's being multiplied to each one of these values to get the next term. So let's discover what that is. So between 2 and 8, if we divide 2 into 8, we have that you're multiplying by 4. Same thing, 8 to 32, you're multiplying by 4 again. And 32 to 128, it's also multiplying by 4. So what we're going to do here now is, since we have the common ratio and we have the terms, let's start to break apart what this sequence really is and identify the correlation that the common ratio has with each corresponding term. So here's the table. So on the left-hand side, on the left-hand column, we have our term number. on the second to the left side, of obviously coming towards your right side, the a of n side, that's the number that you're looking for, whatever number is being identified in the sequence, in this case, whatever is given in sequence A. Then we have our expanded form and then our shortened form, describing an exponential format. So we think of our first term. First term in the sequence, that's going to be 2 from left to right. Excuse me. And then when we're expanding that, it's going to be 2 times 4, except when we write it in shortened form, it's 2 times 4 to the 0 power. So when we write that out, it's going to be 2 times 4 to the 0 power. Now, the reason why it's 2 times 4 to the 0 power, even though 4 is our common ratio, we know that with the first term, in order to get the first term, you're not going to be multiplying by 4. It's going to stay the same. And whenever you multiply, whenever you add an exponent to any given number and you make it 0, it's going to be 1. So 4 to the 0 power is merely 1, so it's going to be equal to 2. So for our second term, we have 8. Now, since it's our second term, we're actually going to multiply our starting term, by our common ratio, the previous term by the common ratio. So 2 times 4, that's also 2 times 4 to the first, and that's how you get 8. For our third term, we have 32. Same thing goes here, except you're going to multiply by another 4 from the starting 2. So 2 times 4 times 4, that's going to give you 32, or 2 times 4 squared. Then, of course, we have our fourth term, 128, and then you just add another multiplier of 4, your common ratio. So 2 times 4 times 4 times 4, that's 2 times 4 to the third. That's how you get 128. And then when we create a rule for this is where I'm going to be explaining this later on in the video, but just to show you a little glimpse of it, a of n is what number we're looking for. That's basically like your y and your x. You're always plugging in values for whatever values you want to describe. So a of n is just a placeholder. That's equal to your common ratio multiplied by, to your starting value multiplied by your common ratio for what's being multiplied to each term, and then it's going to be raised to the n minus 1 power. And I'll explain exactly what that means. Starting off with the explicit formula. The explicit formula is specialized with geometric sequences to find any term in that particular sequence. So you can use it, you find any of the given information, like the starting value, and then of course you plug it in to find any future values. So this is what the equation looks like. A of n equals a of 1 times r raised to the n minus 1. Now you might be a little bit confused. What exactly does that mean? Well, I'll break apart what each term actually means, and then of course we'll go into practice problems correlating each term to its given numerical value in a sequence. So on the left-hand side, we have a of n, which is your nth term, the term that you're actually looking for, what you're trying to discover. Just like x and y are placeholder variables, essentially a of n is the same. Then, of course, we have a of 1, and if you think about a being the sequence itself, a of 1 is the first term in the sequence, the starting term. So like the first sequence we saw, 2 is the starting term. Then, of course, n minus 1, the exponent, what we're raising r2 is going to be our previous term, the previous term to the term that we're actually looking for, the term number. Obviously not the face value, but the term number. And then, of course, we have r, which is going to be our common ratio. Now, when it comes to the previous term, that symbolizes the term minus 1. However, it's going to be the actual face value that's plugged into n minus 1. It's just representing the previous term. And then, of course, r is your common ratio, what you're multiplying to each part of the sequence. Then, of course, we have a recursive formula. It's more specialized to find the previous term, using the previous term, to find the next value in the sequence. So it's a lot cleaner, a lot, more efficient, quicker, and it also helps with larger gaps, obviously with a larger common ratio. So if we take a look here, we have a of n, which is obviously your nth term, the term that you're looking for. We have a of n minus 1, which is the previous term in the sequence to a of n. It's the face value of it. And that's being multiplied by the common ratio, of course. So now let's take a look at some simple practice problems. So let's represent the sequence below with the recursive and explicit. So we'll take the sequence that's given, all the information will be provided, and we'll try and write it in a recursive format and also an explicit format. So we have this sequence here, 750, 150, 30, 6, and also 1.2. So if we identify the difference, it's already indicated that this sequence is going to be a formal sequence, a geometric sequence. So we're going to calculate for one, difference, one common ratio, and that's going to be multiplying by 1/5. Excuse me. So you're multiplying by 1/5 your common ratio. On the left-hand side, we're going to create our explicit formula. So here what we're going to do is, obviously, we're taking a of n on our left-hand side as our placeholder variable that's going to be equal to our, of course, our initial value, 750. That's going to be multiplied by 1/5 your common ratio here, obviously, and then you're going to raise that to n minus 1. N minus 1 is also a placeholder when you're calculating for a certain term in the sequence. Just like we did with arithmetic sequences, you're going to merely plug in those values for n, and then you'll solve as shown. And then, of course, on the right-hand side, we have the recursive format. You don't need the first term, you just need the previous term, and obviously the common ratio. So we have a of n is equal to 1/5 times a of n minus 1, 1/5 being our common ratio, and obviously a of n minus 1 being the previous term. So practice continued. Now we're going to shift between the recursive and explicit formulas to end the video. So we're going to shift between, essentially transfer between the recursive formula, whatever's written in recursive, with the information given. We're going to switch between the explicit and backwards. So we're given an explicit formula here. A of n equals 4 times 8 to the n minus 1 power. We're going to change that to the recursive format. So what we basically did here is we're just rearranging the parts here. All the information that we need from the explicit formula is already in the recursive formula. So if we take a look at it, we know that our common ratio is 8. So we take 8 and we multiply it by our previous term, a of n minus 1. So that's our equation. And then on the right-hand side, we obviously have the opposite. We're going from explicit to recursive. So we have the equation a of n equals 2 times a of n minus 1, 2 being our common ratio. And I also put in there that a of 1 equals 7. Remember, the explicit formula does require you to have, we're going from recursive to explicit. So the explicit formula requires you to have the first term. The recursive formula does not include the first term. So you'll always be given a separate addition of the first term. So we're given here, what's given here is our finalized format for the explicit formula. So we have that a of n equals 7 times 2 to the n minus 1 power. You merely take the first term, multiply by the common ratio, and raise it to n minus 1. Alright everyone, so that'll be it for today's video. I hope you guys enjoyed. This has been AJay Raj here at the eCoreAcademy e-learning platform. Please make sure to like and subscribe and drop a comment down below. Check out our website at www.ecoreacademy.org. Email us at ecoreacademy@gmail.com. Check out all of our socials, Pinterest, Facebook, Twitter, Instagram, TikTok. And also feel free to check out all the other videos and content on this YouTube channel and on the website. We have a lot of great teachers here, so please go and show them some support. I hope you guys enjoyed this video. This has been AJay, and I'll see you guys in the next one. Peace.